I welcome you all to my 39th lecture on digital signal processing, that is UEC 502 for electronics and communication engineering students and electronics and computer engineering students. Now we will discuss finite length MMSE equalizer. In the last lecture, we did derivation of MMSE equalizer for infinite number of tap coefficients. Let us now turn our attention to the case in which the transversal equalizer spans a finite time duration. The output of equalizer in the kth signaling interval is I cap k is equal to summation j running from minus m to m cj pk minus j. Mark it as equation A. As discussed earlier, pk minus j is unequalized input to the equalizer. The MSE for equalizer, that is mean square error for the equalizer having 2m plus 1 taps, is denoted by j bracket m such that j bracket m is equal to expectation bracket magnitude I k minus I cap k square, and that is equal to expectation bracket magnitude I k minus summation j running from minus m to m summation j running from minus m to m cj pk minus j the square. So mark it as equation B as shown on the screen. Minimization of j bracket capital M with respect to the tap weights Cj or equivalently forcing the error Ek is equal to Ik minus I cap k to be orthogonal to the signal samples P conjugate J minus L for magnitude L less than equal to M yields the following set of simultaneous equations. Now summation J running from minus M to M Cj tau Lj is equal to xi L, that is equation C, as I have discussed that minimization of J bracket M with respect to the tap weight Cj or equivalently forcing the error Ek is equal to Ik minus I cap k to be orthogonal to the signal samples P conjugate J minus L yields the following set of simultaneous equations, that is represented by equation C for different values of L, where L is changing from minus M to M. So this is equation C, where tau Lj is equal to XL minus J plus N naught delta Lj for magnitude L minus J less than equal to L, mark it as equation D, and tau Lj is 0 for other values of L minus J. Now xi L is equal to F cap conjugate minus L for L in the range minus L to 0, mark it as equation E, and 0 otherwise. It is convenient to express the set of linear equations defined by equation C in the matrix form. Therefore, we will write equation C in the matrix form as tau vector into C vector is equal to xi vector, where C vector denotes the column vector of 2m plus 1 tap weight coefficients, and tau vector denotes the 2m plus 1 cross 2m plus 1 Hermitian covariance matrix with elements tau ij. Here xi vector is a 2m plus 1 dimensional column vector with elements xi l. Now looking at equation G, we can find the optimum solution of equation G as C vector optimum is equal to tau vector inverse into xi vector. Mark it as equation I. Here C vector optimum is optimum tap weight coefficient, and you know that in the calculation of optimum tap coefficients, there is involvement of metric inversion. Look at this equation I. Now we are concerned about the minimum value of MSE. The optimum tap weight coefficients given by equation I minimize the performance index J bracket M with the result that the minimum value of J bracket M is J minimum M is equal to 1 minus summation J running from 1 minus summation j running from minus m to 0, Cj fk minus j, f cap minus j. Mark it as equation k. Now I can express this summation term in terms of matrix. So I can write j minimum bracket m is equal to 1 minus xi vector dash conjugate tau vector inverse xi vector. Mark it as equation n, where xi vector dash represents the transpose of the column vector xi vector. Here j minimum m may be used to compute the output SNR for linear equalizer with 2m plus 1 coefficients. So we have calculated j minimum for MMSE equalizer using equation n. So I finished this article here, and now I will start the next article, that is fractionally spaced equalizers. In linear equalizer structures, the equalizer taps are spaced at the reciprocal of symbol rate, that is at the reciprocal of the signaling rate 1 by capital T. This tap spacing is optimum if the equalizer is preceded by a filter matched to the channel distorted transmitted pulse. This is very important. This tap spacing is optimum if the equalizer is preceded by a filter matched to the channel distorted transmitted pulse. However, when the channel characteristics are unknown, this is very important line. When the channel characteristics are unknown, the receiver filter is usually matched to the transmitted signal pulse, and the sampling time is optimized for this suboptimum filter. The limitations of symbol rate equalizer are most easily evident in the frequency domain. Let us consider, or let the received equivalent low pass signal is expressed as RLT is equal to summation n in ht minus n capital T plus zt, marked as equation O, which we have discussed earlier also. Here in is the information sample value, h is the response of channel to the input signal pulse, zt is the additive white Gaussian noise. So this equation we have discussed earlier. We denote the output of receiving filter as yt is equal to summation n in xt minus n capital T plus vt as equation P. When the frequency response of the receiving filter is capital H conjugate f, xt is pulse representing the response of the receiving filter to the input pulse ht, and vt is the response of the receiving filter to the noise zt. So in the equation P, I repeat, xt is the pulse representing the response of receiving filter to the input pulse ht, and vt is the response of receiving filter to the noise zt. Now, if tau naught is the transmission delay through the channel, then we sample yt at times t is equal to k capital T plus tau naught. When k is changing from 0, 1 to so on, it leads to y k capital T plus tau naught is equal to yk, and that is equal to summation n in x k capital T plus tau naught minus n capital T plus v bracket k capital T plus tau naught, as shown as equation Q. Here you can see here. So equivalently, yk is equal to summation n in xk minus n plus vk. Now I will expand this equation as equation R, that is ik plus summation n not equal to k in xk minus n plus vk. Now look at this. The first term ik is desired symbol because we have considered x naught is equal to 1. And this term is ISI. Second term is ISI plus Vk, and this is noise term. So this equation R indicates three terms. First is desired symbol, second is ISI, and third is noise. The spectrum of signal at the input to the equalizer may be expressed as capital YTF is equal to 1 by T summation n x bracket capital F minus n by T e raised to j 2 pi bracket F minus n by t tau naught. Mark it as equation S. So you need to go through the sampling article on sampling before sampling first, and then you will go through this lecture, where YTF is the folded or Elias spectrum, where the folding frequency is 1 by 2t. Note that the received signal spectrum in equation S, look at this, is dependent on the choice of tau naught. So it is dependent on tau naught. The signal spectrum at the output of the equalizer is capital CT bracket F into Y T bracket F, where CTF is equal to summation k running from minus m to m ck e raised to minus j 2 pi capital F kt. Mark it as equation U1. For capital omega, magnitude is less than or equal to pi by t. Now the signal spectrum at the output of the equalizer is OTF, that is equal to CTF into YTF. So here OTF is equal to summation k running from minus m to m ck e raised to minus j 2 pi f k t into summation n x bracket f minus n by t into e raised to j 2 pi bracket f minus n by t into tau naught, and this whole is divided by capital T. Mark as the equation U2. In particular, since capital CT omega is equal to CT omega plus minus K omega S because of sampling theorem, with omega S is equal to pi by T, the synchronously spaced equalizer can only act to modify YTF. So look at this, OTF is equal to CTF into YTF, because the spectrums are going to be multiplied. So look at this, the synchronously spaced equalizer can only act to modify YTF. This CTF will modify YTF as opposed to directly modifying capital XF e raised to j 2 pi capital F tau naught. So this CTF will act entirely on YTF, not on the individual term capital XF e raised to j 2 pi F tau naught. It is clear that the symbol rate equalizer can only compensate for the frequency response characteristics of the Elias received signal. So this is the Elias received signal, and this CTF is going to act on this YTF. It is clear that the symbol rate equalizer can only compensate for the frequency response characteristics of the Elias received signal. It cannot compensate for the channel distortion inherent in capital XF e raised to j 2 pi capital F tau naught. So this is very, very important. This is going to form the base of fractional space equalizer. In contrast to the symbol rate equalizer, a fractionally spaced equalizer, that is known as FSE, is based on sampling of incoming signal at least as far as the Nyquist rate. For example, if the transmitted signal consists of pulses having a raised cosine spectrum with a roll-off factor beta, its spectrum extends to F maximum is equal to 1 plus beta by 2t. This signal can be sampled at the receiver at a rate 2F maximum, that is equal to 2 bracket 1 plus beta by 2t, and then pass through an equalizer with tap spacing of capital T by 1 plus beta. If beta is equal to 1, this is case 1. If beta is equal to 1, we would have a 1 by 2t spaced equalizer. And if beta is equal to 1 by 2, we would have a 2 by 3t spaced equalizer. In general, a digitally implemented fractionally spaced equalizer has tap spacing of capital M t by n, where capital M and n are integer, and n is greater than m. Now the frequency response of fractionally spaced equalizer FSE is CT-F bracket F is equal to summation k running from minus m to m ck e raised to minus j 2 pi capital F k t dash. Mark it as equation V1, where t dash equal to capital M t by n. It follows that CT-F can equalize the received signal spectrum beyond the Nyquist frequency Fn is equal to 1 by 2t to Fn is equal to 1 plus beta by t, and that is equal to n by mt. The equalizer input is sampled at the rate 1 by t dash. This is very important. Now the scaled equalized spectrum is Ct dash bracket f into Yt dash f is equal to Ct dash f summation n capital X bracket f minus n by t dash e raised to power j 2 pi bracket f minus n by t dash tau naught. Mark it as equation V2, which is further equal to Ct dash f into summation n x f minus n capital N by mt into e raised to j 2 pi bracket f minus n into capital N by mt into tau naught. As capital XF is equal to 0 for magnitude capital F greater than n by mt, therefore we can express V2. This is very important, as capital XF is equal to 0 for magnitude capital F greater than n by mt. Therefore, we can express V2 as Ct dash f into Yt dash f is equal to Ct dash f into xf e raised to j 2 pi ft naught tau naught. So mark it as equation V3 for capital omega magnitude less than equal to pi by t dash, or capital F magnitude less than equal to 1 by 2 t dash. Now look at equation V3. We observe that FSE compensates for the channel distortion in the received signal before the aliasing effects due to the symbol rate sampling based on equation V3. Thus, Ct-f acts on capital XF e raised to j 2 pi capital F tau naught before aliasing with respect to the output sampling rate. So this is very important fact. Now Ct-f is acting on capital XF e raised to j 2 pi capital F tau naught. This is very important. For FSE, the output is still sampled at the rate T inverse, as the data decisions are made at the symbol intervals. Eventually, FSC output is sampled at the rate 1 by T and has the spectrum capital O T dash bracket F is equal to 1 by T summation K Ct dash bracket F minus K by T into X bracket F minus K by T e raised to j 2 pi bracket F minus K by T tau naught. Mark it as equation V4. Note that equation V4 differs from equation U2 in that it is the sum of equalized aliased components rather than an equalization of an already formed sum of aliased components. We will have a look at U2. Now look at U2. Here CTF is acting on YTF, sum of aliased component. CTF is acting on sum of aliased components. Now here look at V4. Note that equation V4 differs from U2 in that it is the sum of equalized aliased components rather than an equalization of an already formed sum of aliased components. So here it is sum of the equalized aliased components. V4 indicates that OT dash bracket F is sum of equalized aliased components. It is evident that an FSC is capable of much more than compensating for a poor choice of timing phase. Hence, FSC can be configured as the best linear receiver. And so it has found a big application in industrial application in industry. Let us now consider the adjustment of tap coefficients in the FSC. The input to FSC may be expressed as yt sampled at t is equal to t dash k is equal to summation n in x bracket xkt dash minus n capital T plus vkt dash, mark it as equation v5, or yt dash k is equal to y bracket mtk by n, and that is equal to summation n in x bracket k capital mt by n plus nt plus v k capital mt by n, mark it as equation v6. In each symbol duration, FSE produces an output of the form I cap k is equal to summation n running from minus m to m cn y bracket k capital T minus n capital M t by n, marked as equation V7, where the coefficients of the equalizer are selected to minimize MSE. The optimization leads to a set of linear equations for the equalizer coefficient that have the solution C vector optimum is equal to A vector inverse alpha vector, marked as equation V8, where A vector is the covariance matrix of the input data, alpha vector is the cross correlation matrix or vector. Usually a 1 by 2 capital T space equalizer is used in many applications. So the most favorite case is T by 2 space equalizer. So this is the optimum solution, that is C vector optimum is the optimum solution. This optimization leads to a set of linear equation of the equalizer coefficient that have the solution C vector optimum is equal to A vector inverse alpha vector. Quite similar to the previous case. It is quite similar to the previous case. So I finished this article here, and for filtering you can consult these books, but this article is from the book by John G. Prokes on digital communications. The student interested in self-study must go through this book. It's a wonderful book. So thanks for attending this session on DSP. See you in next lecture.